Swayam Prabha. Digital India. Educated India.
It turns out that there is an even more elegant way of finding the force response of a linear circuit to a sinusoidal input. Okay, given that we know the solution to exponential st, and we also know that these are linear circuits. Okay. I will show an RC filter here, but this applies to any linear system of any order. Okay, I will continue with this example, but it could be, I could think of a general system here where I apply Vp cos omega t to some linear system. Okay, so I will get some, let's say Vc1. Okay. So here I am only considering the steady state response parts. Okay. So let us say this Vc1 is a steady state and Vc2 is a steady state response. So Vc1 is the steady state response to Vp cos omega t plus phi. Vc2 is the steady state response to Vp times sin omega t plus phi. Okay. And we know that this follows superposition. Okay. So the steady state responses follow superposition. So what should I do now? What could I do? Let's say I could weight this by some number and this by some other number and add up. That will be the response to weighting this by some number and weighting this by this number. Okay, isn't it? Or if I imagine this RC filter with alpha times this as the input and beta times that as the input, the steady state response will be alpha times Vc1 plus beta times Vc2. Is this part convincing? Right, this is just straightforward superposition. So the interesting thing is now, let's say this is 1 and this is j. Okay, I will take Vp cos omega t plus phi plus j times Vp sin omega t plus phi. This is all in your head. I mean, don't worry about how we get j times Vp as the voltage. Okay. So what is the actual input that you are applying? This is equivalent to applying an input of Vp exponential j omega t plus phi, and the response to that is right. Now the solution to this I already know. What is it? What is the steady state solution to Vp exponential j omega t plus phi for this particular circuit? I have two linear systems. The first one has an input Vp cos omega t plus phi. Second one has an input Vp sin omega t plus phi. The first one has a response Vc1. Second one has a response Vc2. So if I apply to a third system, so maybe I will show those pictures. So let us say the response is Vc1 to Vp cos omega t plus phi. And the response is Vc2 to Vp sin omega t plus phi, and so if I have Vp times alpha cos omega t plus phi plus beta times sin omega t plus phi, the steady state response would be alpha times Vc1 plus beta times Vc2. That is okay. So clearly This works for any alpha and beta. So I will use alpha equal to 1, beta equals to j. So the response to Vp exponential j omega t plus phi would be Vc1 plus j times Vc2. Okay. So what is the response of our circuit to Vp exponential j omega t plus phi? What is the response to Vp exponential st? What was it? The steady state response? Vp by 1 plus SCR exponential st. Okay. So this is nothing but Vp exponential j phi exponential j omega t. Okay. So the solution to this is Vp exponential j phi by 1 plus j omega cr exponential j omega t. Okay, and I can put that phi back there. Okay, I can write it as also Vp exponential j omega t plus phi by 1 plus j omega cr. Okay, the answer I already know. That's the advantage here. I did the superposition. The input turns out to be Vp exponential j omega t plus phi, and the answer to that I already know. Then what? If I write the differential equation separately, this one is Rc dVc1 by dt plus Vc1 equals Vp cos omega t plus phi, and Rc dVc2 by dt plus Vc2 is Vp sin omega t plus phi. The key here is these coefficients are all real. If those coefficients were imaginary, which is a perfectly valid linear differential equation, we couldn't do this. Okay, then you would get cross terms. I mean, this can give you that and so on. The only place we get this square root of minus 1 is where we do the superposition. Okay, we multiply this by 1 and we multiply this by j and then we add it up. Okay, so the only place where this j appears is when it multiplies this one. Because of that, when you compute the response to Vp exponential j omega t plus phi, the real part is the response here and the imaginary part is the response there. Okay, the key thing here is that this is a linear system whose differential equation has only real coefficients. Okay, now of course any circuit will follow that because all our component values are real. Okay, but it's possible to construct differential equations with, I mean, I can just put a j here. You can find the solution to that, but then you can't say that the real part is coming from there. Okay, because you could also get a complex part just because of j that's inside the system. Okay, so this is the real part and this is the imaginary part. This is fine. So this is just a way of superposing cos and sine to get complex exponential, and solutions to complex exponentials in general are simpler algebraically compared to the solutions to sinusoids. They are the same solution of course in spirit, but the formulas look a little more messy because I had this alpha cos omega t plus beta sine omega t and then I had to find the constants and so on. Now this is an easier way of doing it. Of course, while doing this you will get the same answer. So I strongly urge you to try all three methods. Okay, this is first of all a very simple circuit. So you put solution as alpha cos plus beta sine, find the constants. You decompose the cos as exponential plus j omega, exponential minus j omega, find the solution, and finally you do this, you will get the solution. What is the solution then? What is Vc1? What is the forced response? What is the real part of this? If this is the source, R and C, the solution is Vp by 1 plus j omega Cr exponential j omega t plus phi. Okay, this is the forced response. Again, we are only talking about the forced response here. And if you had Vp cos omega t plus phi as the excitation, the response would be the real part of this. So what is the real part of this? The real part of this. Okay. And what is that? Many ways to do it. First of all, I assume you are already pretty comfortable with calculations involving complex numbers. There are two forms of complex numbers. This is known as the rectangular form, where you give the x and y coordinates of the complex number, or the polar form, which gives you the amplitude and the argument or the angle. Okay. Now, both representations are useful. Clearly, this is more convenient for adding complex numbers. This is more convenient for multiplying complex numbers. Okay. So, if I use this here, what do I have? 1 by 1 plus j omega CR. What is the amplitude of this? Amplitude. That is the amplitude, and the argument is minus tan inverse omega CR. Okay, there are so many ways of doing it, or you rationalize so that you get the real denominator and then a complex numerator and so on. Okay, so finally the response to this turns out to be Vp by square root of 1 plus omega CR square and cos of omega t plus phi minus tan inverse omega CR. Okay, so you apply a sinusoid to a linear system. What you get out is a sinusoid of exactly the same frequency. The amplitude will be changed and the phase will be changed. How much the amplitude will be changed and how much the phase will be changed depend on the circuit. Okay, so this is the amount of phase change, right? And this is the factor by which the amplitude is changed. So that clearly depends on the circuit as well as frequency. Okay, so you can also, once you have capacitors in the picture or inductors, you can have frequency selective circuits, that is, circuits which behave differently at different frequencies. Clearly, you can see from this expression itself that if omega is very large, the amplitude of the output will be very small, and if omega is very small, the amplitude is the same as the input. Okay, and very small is compared to 1 by RC. Okay, so if omega CR is much smaller than 1, the output amplitude is Vp. If it's much more than 1, it's inversely proportional to omega. Okay. So the response, the real part of this, has a cosine whose amplitude is Vp divided by square root of 1 plus omega square c square r square, and whose argument is omega t plus phi minus tan inverse omega CR. Okay. Most important thing you notice here is that if you apply a sinusoid to a linear system, the forced response will be a sinusoid of exactly the same frequency. Okay, you cannot generate any new frequencies from a linear system, right? You applied cos omega t, you are only going to get cos omega t. Its amplitude is changed, its phase is changed. That's all. Okay, but this is a very, very important aspect of linear systems that will be useful for everything, both for analysis and measurement and testing. Okay.